One, Chapter 5, Section 5.7, using congruent triangles. Example 1, triangle GHI is congruent to triangle JKL by what theorem? So if we look at the markings on the diagram, we have tick marks indicating that we have 3 pairs of congruent sides. So these are congruent by side, side, side. Can we say that angle H is congruent to angle K? Well, angle H has 2 tick marks on the right and 3 tick marks on the left. Angle K has 2 tick marks on the right, 3 tick marks on the left. They correspond to each other. They do match up. Angle H corresponds to angle K. So yes, we can say that angle H is congruent to angle K once we have said that the 2 triangles are congruent to each other, because then all the other pieces parts must also be congruent. So yes. Is angle I congruent to angle J? Maybe, but we cannot say yes. We have to say no, because we don't know if angle I is congruent to angle J. We know that angle I is going to be congruent to angle L, angle I, angle L, last, they match up. But angle I and angle J do not correspond to each other. We don't know if they are congruent. No. So what are we talking about here? We're talking about the concept of corresponding parts of congruent triangles are congruent, or CPCTC. You're allowed to write that, that abbreviation as a reason in a proof, but if I ask you during class, what does CPCTC stand for, or what is the reason, and the answer is CPCTC, I want you to say out loud, corresponding parts of congruent triangles are congruent, because I want you to learn what the words are, not just the abbreviation. Okay, so example 2 here, we're going to do an actual proof where we're going to use CPCTC. To use CPCTC, corresponding parts of congruent triangles. We have to have congruent triangles in order to use CPCTC. Well, unless we're given that the triangles are congruent, we're going to have to prove that the triangles are congruent first, and then we can use all those pieces parts that we didn't know before were congruent must now be congruent. Okay, so in example 2, angle M is congruent to angle P. M is congruent to angle P. X is the midpoint of segment MP. What does that mean? It means if X is the midpoint of segment MP, then X must be splitting segment MP into 2 congruent segments. Now, what I'm marking here is a conclusion. That is not given information. We're given that it's the midpoint. We conclude that MX is congruent to XP. So it's going to need its own line in the proof. If we look at the diagram, is there anything else that we can look at the diagram and know or conclude from the given information or from the diagram? The answer is yes. We can conclude that angle MXN is congruent to angle PXO by the vertical angles theorem, BAT. So once we know that these 2 angles are congruent, now we should have had enough practice at this point to look at this diagram and the way it's marked up and to recognize right now that these 2 triangles are congruent. These 2 triangles are congruent by angle, side, angle. Once we know the 2 triangles are congruent by angle, side, angle, all the other pieces that we don't have marked as congruent but correspond to each other have to be congruent. Specifically, MN up here corresponds to PO, and they will have to be congruent by CPCTC. So the rest is just writing it out. Statements, reasons. Statement 1, to rewrite the given. You have to rewrite the given. I'm just writing the squigglies. Statement 2. Well, the second thing that we did was when we said X is the midpoint of segment MP, I concluded that segment MX was congruent to segment XP by the definition of a midpoint. I know what a midpoint means, and that's our conclusion. Statement 3. Statement 3 was to talk about these 2 pairs of this pair of vertical angles. So angle MXN congruent to angle PXO by the vertical angles theorem. I'm abbreviating that VAT. Statement 4 was to conclude that the two triangles are congruent. Triangle MXN is congruent to triangle PXO, making sure I'm putting the letters in the correct order, the vertices in the correct order, because angle M has to match up with angle P. Angle M matches up with angle P. Statement 4, we knew that these two triangles were congruent by angle-side angle. Once we have the two triangles congruent, we can say all the other pieces parts that we didn't know were congruent before are now congruent, specifically the parts that we are trying to prove. Segment MN is congruent to segment PO. And that reason, CPCTC QED. So that is example 2. Example 3. Slide it like this so we can still see it. Okay. Write proof. Here we have AE and BD bisect each other. Well, what does that mean? It means that they intersect each other at each other's midpoints to create congruent segments. So in other words, AE is broken up into AC and CE, which are congruent to each other. BD is broken up into BC and CD, which are congruent to each other. Looking at the diagram, and so again, I'm going to have to write out those statements in their own places in the proof, because saying that AC is congruent to CE is not what the given statement says. So the reason there is not given. When we look at this diagram, there's one more thing that we can conclude. We can conclude angle ACB is congruent to angle ECD by the vertical angles theorem. Now when we look at this diagram, we need to recognize that these two triangles are congruent. These two triangles are congruent by side, angle, side. Now that we have the two triangles congruent, all the other pieces that we didn't know were congruent before are now congruent. Specifically, and I can go with either angle A congruent to angle E, or angle B congruent to angle D. I could even say AB is congruent to DE, but that's not going to actually help me looking ahead to what I'm trying to prove. I'm trying to prove that line AB is parallel to line DE. To prove lines parallel, we had 5 ways to prove lines parallel in the previous chapter. We had the converse of the corresponding angles theorem, converse of the alternate angles theorem, so on and so forth, right? Converse of the consecutive interior angles theorem, converse of the exterior angles theorem, alternate exterior angles theorem, and we had the definition of parallel lines. So we had all those different ways of proving lines were parallel. So now we're going to use one of those to prove that these two lines are parallel. So if we take a look, again, I'm going to use either angle A congruent to angle E, or angle B congruent to angle D. I'm going to use angle A congruent to angle E, 2 arcs. I used 1 arc from the vertical angles. Why? Because they form the Z-like shape that marks all alternate angles. Angle B and angle D also make the Z-like shape, and they are also alternate angles. That's why I had a choice. It really doesn't matter which of the two that I go with to prove the lines are parallel. Once I say that these two angles are congruent, I'll be able to say these two lines are parallel by the converse of the alternate angles there. So the rest is just writing it out, and I'm actually going to pull out a blank piece of paper here and write it out. So this is example 3. Statements, reasons. Statement 1 is to rewrite the given information. Statement 2 is what did we conclude after that given information? We concluded AC was congruent to CE, BC is congruent to DC. Technically, I'm surely going to take an extra step on this. Technically, we are concluding that C is the midpoint of segments AE and BD. That's the definition of a segment bisector. And just like in example 2, now that I know that C is the midpoint, now I can say AC is congruent to CE and BC is congruent to CT. Definition of midpoint. The next thing that we did, referring back to my diagram, is we said the vertical angles were congruent to each other. So statement 4, angle ACB congruent to angle ECD. Vertical angles theorem, abbreviated VAT. Just make sure that that is focused. There we go. Statement 5 is, now that we have the vertical angles, we have these two triangles congruent by side angles side. So triangle ACB congruent to triangle ECD, side angle side. Statement 6, and I'm going to say angle A congruent to angle E, or, and you don't have to put the or, you don't have to put both, you just pick one of these. Angle B congruent to angle D, and this is where we use the new information from this unit, CPCTC, which is the abbreviation for corresponding parts of congruent angles are congruent. Statement 7, final statement, line AB is parallel to line DE, what we were trying to prove, and the reason is converse of the alt int angles theorem. QED. All right, so that was example 3. Back over here to example 4. I think I might be able to fit example 4 in here. We'll see. Angle D is congruent to angle B. Let's mark that up in our diagram. Angle D congruent to angle B. Angle DAC, DAC, is congruent to angle BCA. 2 arcs. 2 arcs. If we look at the diagram, is there anything else that we can conclude? Because I've done all the given information. There's one more thing that we can conclude. AC is congruent to itself by the reflexive property. Now when we look at the diagram, I see angle, angle, side. Angle, angle, side. Order is important here. The side is not the included side, so it's not angle, side, angle. It's angle, angle, side. If it were the included angle, it would, included side, it would have been AD congruent to BC, but it's not. It's AC is congruent to AC. So the two triangles are congruent by angle, angle, side, making these two corresponding sides, AB and CD, congruent to each other. So I think I can fit this in here. Statements, reasons. It's going to be tight. You know what? I'm going to slide the reasons column over to the right a little bit here. See if I can fit it in now. All right. Statement 1, rewrite the given. I'm not rewriting, I'm just putting the squigglies. You have to rewrite them. Statement 2 was when we said segment AC was congruent to itself. AC congruent AC. Reason, reflexive property. Reflexive property. Statement 3. Once we said AC was congruent to itself, we had angle, angle, side. So the two triangles were congruent to each other. Triangle DAC congruent to triangle. I'm going to make sure I get the order right. D matches up to B, A matches up to C. So BCA. And that reason was angle, angle, side. Once we had the two triangles congruent, then we had enough information to prove what we were trying to prove all along. Statement 4, segment AB is congruent to segment CD. And our reason, corresponding parts of congruent triangles are congruent. C, P, C, T, C, QED. Now, I'm going to change up the way I normally do these videos. Normally I'm writing out all the answers and doing problems along, but you can see that we have a lot of proofs in this unit. Some of them are extremely long. Most of them are very tricky to do and to understand. So what I'm going to do now is I'm going to actually switch over to the solution set, and I didn't have solutions for all of them. I will by the end of the video, but I didn't prior to that. So example 5, I've already given you access right here. So it's moved. Okay, let's make that a little bit better. Okay, example 5, I've already got it typed up. And I've shared this document with you on Google Classroom already. So it's going to be, I'm just going to go through it, and it's going to save us some time instead of watching me rewrite all of these answers in proof forms. It's going to be just a lot quicker. So WO is congruent to ZO. Let's mark that up in our diagram. WO is congruent to ZO. Okay. XO is congruent to YO. XO congruent to YO. Okay, good. Now, when we look at the diagram, we want to see, is there anything else that we can conclude? Yes, there is. We can conclude that angle WOX is congruent to angle ZOY by vertical angles theorem. So now when we look at our diagram, we're going to say, well, what can we conclude now? You have to be able, at this point in your geometric career, looking at the diagram the way it's marked up right now, it has to just jump out at you that this is side angle side. These two triangles are congruent by side angle side. Once the two triangles are congruent by side angle side, then all the missing pieces of information that we didn't have before, specifically angle W and angle Z, which correspond to each other, must be congruent to each other by CPCTC. So marking up the diagram, hopefully you can see how we get to side angle side and how we can get to angle W congruent to angle Z. The rest is just writing it out. Rewrite the given information. The two angles are congruent by vertical angles theorem. The two triangles are congruent by side angle side. These two angles are congruent by CPCTC. And that's how the ones that I've got written out and done, that's how I'm going to go through them. Like example 6. Example 6 is actually the exact same diagram, but this time we have different given information. Okay, this time we're given angle Y. X is congruent to angle Y. XO is congruent to YO. And that's all the given information. Now, when we look at the diagram, we still see vertical angles. These two triangles are now congruent. You have to look at this diagram and marking up the diagrams are the key. If you mark up the diagrams correctly, you have to then look at the diagrams and be able to recognize these two triangles are congruent by angle side angle. We have a pair of included congruent sides, so this is angle side angle. Once we have the two triangles congruent by angle side angle, all the other pieces, parts that we didn't know before, specifically WO congruent to ZO, WO and ZO correspond to each other, they have to be congruent. So now we write it out. Rewrite the given information. Angle WOX is congruent to angle ZOY, vertical angles theorem. The two triangles are congruent. WOX is congruent to triangle ZOY, angle side angle. And once we have the two triangles congruent, then the corresponding parts, WO corresponds to ZO, have to be congruent by CPCTC. That was example 6. Example 7. All right. SK is congruent to NR. SK congruent to NR. SN congruent to KR. SN congruent to KR. Okay. Our goal is to prove that the same pairs of segments that we're just looking at a second ago as congruent, we want to prove that they are parallel. So that means we got to find a pair of corresponding angles, alternate interior angles, or consecutive interior angles, or alternate exterior angles that we can prove either being congruent or supplementary in the case of consecutive interior angles. In this case, we're going to find alternate interior angles, and they're going to end up being congruent to each other. So, I've marked up the diagram with the given information. Is there anything else in the diagram that we can conclude? The answer is yes. Side SR is congruent to itself. Once we mark that up in the diagram, now we have to be able to recognize side, 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 side. These two triangles are congruent by side, side, side. Once the two triangles are congruent by side, 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 if I want to prove SK is parallel to RN or NR, I need to know angle 1 is congruent to another angle in this diagram, and that's going to be angle 3, because it makes the alternate angle, makes that Z-like shape, so that we now know that SK is parallel to NR by converse of the alternate angles theorem. Similarly, I'm going to turn the diagram just a little bit so we can see it here. Angle 2 is congruent to angle 3 by CPCTC, and they make the Z-like shape, making SN parallel to KR. And the rest is just writing it out. So, rewrite the given information. Given. SR is congruent to SR. We wrote that as reflexive property. That gave us the two triangles being congruent by side angle side, which gives us angle 1 congruent to angle 3 by CPCTC, and angle 2 congruent to angle 4 also by CPCTC. Since these two pairs of angles are congruent, then these lines are parallel by the converse of the alternate angles theorem. There's a typo there. Okay, so that was example 7, and I'm going to come back to these because we jump down to example 12 in the selected answer key. So I'm going to move this off to the side, but I'm going to come back to it in a minute. Now, example 8 is an interesting example for a couple of reasons. One, it's a neat little story, and 2, you're going to click on, this is a link, okay? This is an Easter egg. So if you click on this anywhere here, it will bring you to a video to watch. Now, after you've watched the video, I will post in Google Classroom a reflection assignment. It is not posted yet, but it will be. When it is posted, you'll have a week to write out probably about a week, 350 or more word reflection on this video. This video is about Napoleon's disastrous campaign going into what was Russia, then became the Soviet Union, and is back now to being Russia again. So, but this problem is related to this campaign, because and you'll see in the videos, in the video, when they have to cross a river, any of you that have ever done any sort of hiking at all know that crossing even a small brook or a stream or a river can be difficult. Now imagine crossing an entire river with an army. Logistically, it is very, very difficult. It's dangerous. And you'll see in the video that there are a few river crossings where Napoleon loses quite a few of his soldiers to the accidents, the perils of crossing a river. So, history. According to legend, one of Napoleon's officers used congruent triangles to estimate the width of the river. On a riverbank, the officer stood straight and lowered the visors of his cap. So I grabbed a baseball cap. Now, imagine that the officer's cap has a visor on it, similar to the visor on a baseball cap. So what he's doing, you can see he is standing next to the river edge, and he looks across the river to the other river bank. Now, when he's looking across the river, he tips the brim of his cap down so that now it's blocking part of his view. So the tip of the cap, the tip of the brim of the cap, is now touching visually the other bank, the other side of the river. Okay? So I wanted to give you the visual of what he's doing. So the officer's got his cap. He tips it down as he's looking over the water until the cap is blocking out the other river bank, and he can only see the other edge of the water. He then turned and noted, so he turns his body, but he's careful to keep the angle of the hat the same. He doesn't change the angle of the brim of his cap. Okay, so he turns and he looks and he notes, what does he see? So now he's looking out over the land. You see here he's looking out over the land, and where is the brim of his cap touching the ground out in the distance? Okay, so he marks that spot. He turned, noted the spot on his side of the river that was in line with his eye and the tip of the visor. The officer then paces out to that spot and declared that distance to be the width of the river. Using congruent triangles, prove that he was correct. How did he know that that definitely was the same as across the river? How does he know that EG is congruent to EF? Okay, well, he's going to use congruent triangles and CPCTC. There are a few things that we're going to have to assume. We don't like to make assumptions in geometry, but in this case, I think we can let it slide. One, we're going to assume that when he is standing, looking over the land, he's standing straight up and down. We're told that he's standing straight up and down, but we're also assuming that he's not leaning forward or leaning back when he's looking over the water or when he's looking over the land. So angle GED is congruent to angle FED. We're going to assume that he doesn't change the angle of the brim of his hat. Now, it's a little hard to do, but I bet you if he does it a couple times and checks it, he's probably going to be pretty close. He's looking for a rough estimate here of the width of the river. He's not looking for exact numbers. So it's probably safe to say that the brim of his cap is at the same angle over the water as it is over the land. And the final assumption that we're going to make is that he does not grow or shrink during this process. He remains the same height when he looks over the water as he is when he's looking over the land. So now, if we look at the diagram, I know it's a little hard to see with the pencil markings, but these two triangles, triangle EFD and triangle EGD, are congruent to each other by angle, side, angle, angle, side, angle. Once the two triangles are congruent to each other by angle, side, angle, FE has to be congruent to EG by CPCTC, and the rest is just writing it out. Statements, reasons. Statement 1, rewrite the given information, which I have written out for you here. DEG and DEF are right angles. Okay, so actually, because he's standing straight up and down, we'll mark those as right angles to be consistent with the given information. And angle EDG is congruent to angle EDF. That's the angle of the brim of his cap. And what do we know about all right angles? We know all right angles are congruent. So angle DEG is congruent to angle DEF. All right angles are congruent, or right angles congruence theorem. Okay, statement 3. What else do we know? We already said it. DE is congruent to DE. DE, congruent. DE, reflexive property. Statement 4, triangle. Let me get the letters right. Let's go FED. Triangle FED, congruent to triangle GED. Statement 4, that was angle, side, angle. Statement 5, FE or EF is congruent to EG by CPCTC QED. That was example 8. Example 9 is just a quick exercise to get you to realize why we're going to need this next piece of information. So, how many triangles are there in the diagram? Identify all the triangles overlapping and non-overlapping, and which triangles appear to be congruent. So I'm going to group them as we count them. And I'm going to tell you right now, there are more triangles in this picture than you will initially think. Very few students guess the correct number. Very few students, even after counting, get the correct number. There's just a lot more triangles than you originally will think. So let's start with the smallest ones. So triangle, screen, yeah. XWT, VWT, VUT, ZUT, ZYT, and XYT. Okay, so we should be up to 6 triangles so far. So that's a group of triangles that appear to be congruent. And if this triangle is equilateral, then they will be. All right, the next group of triangles is usually one that some people miss, and then the group after that will be a group of triangles that the other people miss. People usually miss one or two of these groups. So we're going to go with triangle XTV. That is a common triangle to miss. Triangle XTV would be congruent to triangle VTZ, which is going to be congruent to triangle ZTX. So we have those three triangles. And if you got those, a lot of the people who get those miss these next ones. These next ones, we're going to go with triangle XZW. That is a very common one to be missed. Triangle XZW appears to be congruent to triangle VZW. VZW, which gives us now VXU is in that same category, triangle VXU, and triangle ZXU, and now we've got triangle ZVY, ZVY, and triangle XVY. So there's 6, 9, and then another 6, that's 15. There are actually 16 triangles. This next one is not congruent to any other triangles. It is a very common one to miss, and that is triangle XZV, the biggest triangle of them all, which is a total of 16 triangles. Now, what is the point of this exercise? The point of this exercise is to say that even though this diagram is not overly complicated, there's a lot of triangles going on here. There's 16 different triangles going on here. There's different sets of triangles that match up with each other. Triangle XVY matches up with triangle XZW. Triangle XTV matches up with triangle ZTX. There's a lot of different things going on in this fairly simple diagram. So this leads us into using overlapping triangles in proofs. Some triangle relationships are difficult to see because the triangles overlap. Overlapping triangles may have a common side or angle. You can simply work with the overlapping triangles by separating and redrawing those diagrams. That is oftentimes a good piece of advice. It's not always going to work, but oftentimes it's going to help. So separate and redraw overlapping triangles. Identify common angles and sides. That's important because before you separated them, they were common angles and sides. After you separate them, they're usually not. But you got to remember that they are still common angles and sides before you separated them, and we can use the reflexive property to say that they're still congruent. So that leads us into example 10 here. So example 10, I'm just going to do the diagram on this page, and then I'm going to grab a blank piece of paper to actually do out the proof. So BA is congruent to DE. Let me mark that in the diagram. BA is congruent to DE. BE is congruent to DA. If we look at that, we should see a problem with marking this in the diagram. This becomes tricky. If I mark it like this, it may look like that BC is congruent to DC. How else can I mark it? I don't know, man. Try to do something like this. I don't know, one here, one here, one here, one here. That's just messy. That doesn't work. So, marking up the diagram the way it is, we can't even do it. Okay, we can't even do it. Our goal here is to prove angle BEA, this angle down here, is congruent to angle DAE, this angle down here. Our goal is to prove those pairs of angles are congruent. Well, that's tricky. We need to know which triangles we want to prove to congruent so that we can use CPCTC to prove these angles are congruent. So, how many different triangles are there in this diagram? Very simple diagram, and there's more triangles than you think. The 3 non-overlapping ones, and then you've got triangle BAE and triangle DEA. There's 5 triangles in this diagram. Very tricky. Which pair of triangles, which 2 triangles do we want to separate and redraw so that we can prove these 2 angles are congruent? Well, and this isn't guaranteed, but it helps if you can separate the triangles that have all the given information and also have what we're trying to prove. If you can find a pair of triangles that fits both of those, that's awesome. That's hopefully going to make things a lot easier for you. So, is there a pair of triangles that has BA and DE, BE and DA, and angle BEA and angle DAE in them? The answer is yes. So I'm going to separate and redraw triangle BAE and triangle DEA. Now, it's a horrible drawing, I apologize, but I'm just doing this quickly. Now when I go to mark up our diagram, BA can go into DE, BA can go into DE, BE can go into DA, BE can go into DA. Now I can mark up that BE and DA perfectly. Okay, our goal is to get angle BEA, this one, can go into angle DAE, this one. Okay, now, so that was step 1 of the hints, separate and redraw. Identifying common angles and sides. Remember I said in the beginning that sides and angles that were common before I separated them, they're still common. Because I redrew it doesn't mean that they're no longer common. Which ones are still common? Right here. Side AE, side AE. AE is still congruent to itself by the reflexive property. Once I mark that in the diagram, now you can see these 2 triangles are congruent by side, side, side. It's pretty obvious now. And that these pair of angles are congruent by CPCTC. So I'm going to rewrite that. I'm going to grab that piece of blank paper here. And this is example 10. Example 10. Statements, reasons. Statement 1. Redo the given. Statement 2. It's actually a super quick proof because the toughest part in this proof was knowing which triangles to separate and redraw. But once you actually write out the proof, here I have side, side, AE congruent to AE by the reflexive property. Side, side, side. Statement 3. Triangle BAE congruent to triangle DEA, side, side, side. Statement 4. Angle BEA congruent to angle DDAE, CPCTC. Corresponding parts of congruent triangles are congruent. QED. Alright, that was example 10. Example 11. Example 11 is right here. Okay. Hopefully we'll see if I can fit it in here. If not, I might have to go over to the blank piece of paper. Because this is a challenging one. Alright, angle 1 can go into angle 2. Mark that in that diagram. Angle 1 congruent to angle 2. Okay, good so far. BD congruent to BE. Okay, BD, BE. Good so far. Angle 3 congruent to angle 4. Okay. We're safe so far. I don't have to separate and redraw anything. Our goal is to get triangle DAF congruent to triangle ECF. I've already got a pair of angles. That was pretty good. I got vertical angles here. I got two pairs of angles. I'm angle side or angle side angle. I'm either going after angle side AF congruent to side FC, side DA congruent to side EC, or side DF congruent to side EF. Side DF congruent to side EF. That's the way to go, because if we look at the original given information, look at these two triangles right here. Side, angle, FB congruent to FB, side, angle, side. DF congruent to EF by CPCTC, because they are two sides of these two triangles. I already said 1, 2, 3, 1, 2, 3. Vertical angles, I have angle, side. The rest is just writing it out. So let's do it. Statements, reasons. Statement 1, rewrite the given. Statement 2. All right, so what was the next thing that we did? Side, angle, side. FB, B, not D, congruent to FB. Flexive property. Okay. Triangle. Statement 3. Triangle. BDF. BDF. Congruent to triangle BEF. BEF. By side, angle, side. Now that I have these two triangles congruent by side, angle, side, DF is congruent to EF. DF congruent to EF. Corresponding parts of congruent triangles are congruent with CPCTC. These two angles are congruent. Statement 5. Angle DFA congruent to angle EFC. Vertical angles theorem, VAT. And statement 6, that we're trying to prove in the end, triangle DAF congruent to triangle ECF, and that was angle, side. Angle, side. That was example 12. Now, I'm going to go back to the already done out ones. Save us some time. So example 12. Sorry, that was example 11. We're on to example 12 now. Okay. So, marking up a diagram. Angle 1 is congruent to angle 2. Angle 1 congruent to angle 2. Angle 3 is congruent to angle 4. Angle 3 is congruent to angle 4. Looking at that given information, as I've marked up the diagram, what else can we conclude? LM is congruent to itself. LM is congruent to LM by the reflexive property. Our goal is to get M to be the midpoint of segment JK. My goal is to get M to be the midpoint. So if that's true, then I have to prove JM congruent to MK. I'll just prove these two triangles are congruent by angle, side, angle, angle, side, angle. JM is congruent to KM by CPCTC. So, rewrite the given information. LM is congruent to itself by the reflexive property. The two triangles are congruent by angle, side, angle. Notice that I've got the order of the letters correct so that JM matches up with KM, CPCTC. Once these two segments are congruent to each other, then we can say M is the midpoint of segment JK by the definition of a midpoint. So that's example 12. Example 13. Again, marking up the diagram. It's the same diagram, different given information. I'm sorry, same given information this time. We're trying to prove something different. So angle 1 is still congruent to angle 2. Angle 3 is still congruent to angle 4. And LM is still congruent to itself. So nothing has changed through the first three statements. But our goal is to prove triangle JKL is isosceles this time. JKL is isosceles, so I need to know that JL is congruent to KL. JL, first and last, KL, first and last, they match up. Corresponding parts of congruent triangles are congruent, CPCTC. Triangle JKL is isosceles by the definition of an isosceles triangle. Example 14. Example 14 is actually a very challenging problem to do on your own, straightforward. It's going to look a lot quicker and easier because it's already written out for us here, but I'm here to tell you that this is not an easy problem. There are two different ways you can do this. You can do it with some angle addition. It makes it a little bit harder to do with angle addition. I went with segment addition instead because it was a little bit easier. All right, angle L and angle P are right angles, or 90 degrees. We'll mark those in our diagram here. MN is congruent to QR. MN is congruent to QR. And LR is congruent to PN. LR is congruent to PN. Okay, so our goal is to get triangle LMR congruent to triangle PQN. And if I remember correctly, yes, there are 5 ways to prove triangles congruent, as we know from the earlier unit. Side, angle, side, angle, side, angle, 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 side, and HL. The second I see that we have right triangles, I look for HL first. It's not always going to be HL, sometimes it's side, angle, side, but if I see a pair of right angles, I'm looking for HL first. So I already have a pair of L's. NP and LR are legs. What I don't have are the hypotenuse. So triangle LMR, MR is the hypotenuse of that triangle, and in triangle PQN, QN is the hypotenuse in the triangle on the right. So I don't have those being congruent to each other, but what I do have, I've got QR congruent to NM, and I have RN congruent to itself, and that's going to help me because I have 1 tick mark, 3 tick marks, 1 tick mark, 3 tick marks. NR is made up of NM and NR. QN is made up of QR and RN. So if we do some segment addition, so rewrite the given information, RN is congruent to itself, reflexive property. And now we get into the segment addition postulate stuff. QN is equal to QR plus RN. RM is equal to MN plus RN. That's pretty straightforward. What I can't do is jump straight to QN is congruent to RN. I can't do that. Okay, I got to do this statement here. I have to say QR, which comes from here, QR plus RN, which is here. So I'm going to take this statement. QR is equal to MN Rn. That's this statement. Just spreading it out and using an equals instead of congruence. And I'm going to add to the QR and the Mn this statement. I'm adding equal things to the left and to the right hand side. So if I add an Rn to the left, and if I add an Rn to the right, I've kept the equation balanced. I get this new statement, and the reason that I can do that is the addition property of equality. Now, QR plus Rn is equal to Qn, so I can substitute. Instead of writing QR plus Rn, I can write Qn. Instead of writing Mn plus Rn, I can write Rm. Substitution property. Angles L and P are right angles. Definition of a right angle. They're both 90 degrees. They are right angles. If I'm going to use the HL, I got to say that we have right angles. If I'm going to use HL, I've got to say I have right triangles. Triangle LMR and triangle PQN are right triangles. Definition of right triangles. Therefore, these two triangles are now congruent by HL because we have stated that the H's and the L's were congruent to each other. All right, that was example 14. Moving on to example 15. Example 15 looks simple. It is deceptive. This is not an easy proof at all. It looks a lot like, where did it go? Example 15. No, sorry. Looks like one we did not that long ago. Where did it go? Oh, example 15 looks a little bit like example 14. Similar. Flipped upside down, different letters, but it looks similar to example 11. And example 11 was not too horrible, wasn't too challenging. It was 6 statements. A little tricky to see it, but it was definitely doable. Example 15, though. Example 15 is a significantly more difficult proof to do. Let's see if we can get through it. All right. PK is congruent to PM. PK congruent to PM. So far, I can mark that in the diagram. All right, we're good so far. KY is congruent to MZ. KY is congruent to MZ. We can mark that up in the diagram. What else do we know in this diagram? Our goal is to get angle 1 congruent to angle 2, right? That's our goal. Is there anything else that we know in this diagram? Well, I see a pair of vertical angles here and here. That might help. I see XP congruent to itself. That might help. These are things that I'm looking ahead to see if those are going to help us along the way. Okay, so if I want to go after, say, if I wanted to go after this triangle, KXP and MXP, I have side and a side, and I have another side here, pair of sides. I have side and side, so I could go after side angle side, I could go after side side side. If I go after side angle side, I would have to have proven that angle 1 is congruent to angle 2. Well, that's what I'm trying to get in the end, so I'm not going to be using side angle side to prove these two triangles congruent. Maybe I can prove those two triangles congruent by side, side, side. Because I have PM congruent to PK and XP congruent to itself, maybe I can get XM congruent to XK. Possibly. If I can get XM congruent to XK, then I'll have side, 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 and I'll have these two triangles congruent. XK and XM, they're parts of these two triangles here. Possibly I can get these two triangles congruent since I have a side and a side. I have angles from the vertical angles, so maybe I can get these two triangles congruent by angle angle, side, angle, angle, side. Maybe I can get these two triangles congruent by angle, angle, side, which would get me kx congruent to xm, CPCTC, which would get these two triangles congruent by side, 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 which would get these two angles congruent by CPCTC. So that's a possibility. What's another possibility? So I'm not sure if I can get these two triangles congruent to each other. Maybe I can, maybe I can't. To get these two triangles congruent to each other by angle, angle, side, angle, angle, side, I need to get this angle, y, congruent to this angle, z. How am I going to do that? So I'm working the problem backwards. Okay, I'm going from what is it that I want to prove back to what do I know and see if I can get the two to meet together. So how can I get angle y congruent to angle z? Are there any other triangles that angle y and angle z are in? And the answer is yes. And this is the tricky part of this problem, of this proof, is I have this triangle here. This is P, Y, M, and this triangle here. And this is triangle P, K, Z. Okay, and flip that over, sorry about that. So why did I choose these two triangles to separate out? Well, one, they've got angle y and angle z in them. Two, they have KP and MP, just recopying those from the original. They also have YP, PZ, YP, PZ. YP is KP plus KY, and PZ is PM plus MZ. We know that those pieces parts are congruent, and what we just recently did in the previous problem, so we can use some segment addition to get these two added together, these two added together, so that YP will be congruent to YZ. They're going to be eventually. But that just gives me side, 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 side. So I'm going to mark them like this. Even though we haven't done the legwork yet, that's going to show up in the proof over here, where we actually add those segments together to get them to be equal to each other. I've got a side and a side, so it's either side, 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 or side, angle, side. If it's side, 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 I'd need to know something about ym, which means I would need to know something about yx and xm. Well, yx, that's part of the small triangles. See, well, x, those are part of the small triangles that we're going to prove congruent after we've gotten these. So we don't know anything about them. XM, XK, we said we needed those for later on down the line after we've proven these two smaller ones congruent. So we don't have anything about those, so it's not YM and KZ. What else do we know? Well, let's back up to the hints. Separate and redraw. I did that. Identify common angles and sides. We haven't done that yet. We're going to use those common angles and sides with the reflexive property to prove these triangles are congruent. So, what's the common angle and or side? Well, we took this triangle here, YMP, P, ZPK, angle ZPK, and angle YPM, they're congruent by the reflexive property. Now I have side, angle, side, side, angle, side. Once I've got side, angle, side, then we can say angle Y congruent to angle Z. Once we've got angle Y congruent to angle Z and our verticals, 1, 2, 3, 1, 2, 3, now we've got angle, angle, side, angle, angle, side. We've got these two triangles congruent by angle, angle, side. Once we've got these two triangles congruent by angle, angle, side, now I've got my XK and my XM. We're at 4 tick marks now. Fortunately, 1, 2, 3, 4. 1, 2, 3, 4. And I'm going to go with 5 tick marks on XP. Can't go into itself. 1, 2, 3, 4, 5 tick marks, giving me side, 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 side. And once we've got side, 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 angle 1 is congruent to angle 2, CPCTC. I'm not going to mark it. That would be 4 arcs. Rest is writing it out. Rewrite the given information. That segment addition postulate stuff that we talked about early on. PK is plus YK is equal to YP. PM plus MZ is equal to ZP here. And then what we did in the previous problem, we have to do it again. We're going to take this PK plus is equal to the PM, and we're going to add to it the KY and the MZ, because these are congruent. If I add KY to the left, I have to add something equal to the right, and MZ is equal to it, keeping the equation balanced. That gives me this statement here. Addition property. Now I can substitute YP goes in place of the PK and the KY. ZP goes in place of the MP and the MZ. And we don't actually need to go to this step. I'm just doing it to say that their definition of congruent segments, they are congruent. They're equal in length. They're congruent. All right. Angle YPM is congruent to angle ZPK, reflexive property. That was the common angles that we had separated and redrew over here. That's the reflexive property, giving us these two triangles congruent by side, angle, side, side, angle, side. These two triangles are now congruent by side, angle, side. Once the two triangles were congruent by side, angle, side, that's when we said angle Y was congruent to angle Z, CPCTC. Once we get the two angles congruent by CPCTC, and this another pair of angles, YXK and ZXM, congruent by the vertical angles theorem, then we have these two small triangles in the upper left and the upper right congruent by angle, angle, side. Once you have the two triangles congruent by angle, angle, side, then we have angle, I think I did it differently. I don't need to say angle YMP congruent to angle ZPK, ZKP, YMP. I can. I don't need to. The way I did it, so if I use the two CPCTCs, then I have this angle here and this angle here, which was here and here. I don't use the XP reflexive. So the way I wrote it and marked it up in the diagram, instead of doing this, I would add in another line saying XP can go into XP reflexive property. It's still the same number of statements. Sorry. So instead of saying YMP can go into ZKP, we would say XP can go into itself by reflexive property. It doesn't matter which of these two ways you go. You're either going to go with side, angle, side, or side, side, side. If you go with the angles, you're going with side, angle, side. If you go with XP congruent to XP, it's side, side, side. And then you have these two angles congruent by CPCTC. That was example 15. Example 16. This is a really good proof to go through, because this is one that shows up a lot. It's good practice. We see this type of a proof quite often. This diagram shows up a lot. So let's go to it. Angle 1 congruent to angle 2. Angle 1 congruent to angle 2. Okay. Angle 3 congruent to angle 4. 3, angle 4. Our goal is to prove TU is congruent to TW and TUV is congruent to TWV. So our goal is to prove this side's congruent to this side, and this angle here congruent to this angle here. Okay? So, the way I have the diagram marked up, I already have a pair of congruent triangles. Because SV is congruent to itself, I have these two triangles congruent by angle, side, angle. That's helpful. SV congruent to itself. The two triangles are congruent by angle, side, angle. Okay. Now, a lot of people will then say US is congruent to SW and TS is congruent to itself, and then they're going to get this angle UST, WST congruent to each other by some angle addition, partial, and then subtracting angles, and eventually you can do it that way. And that's going to get you TU congruent to TW, because you're going to have side, angle, side. CPCTC is going to get you TU congruent to TW. And then you're going to have to say that angle TUS is congruent to angle TWS. And we have to add that to angle VUS congruent to VWS. And then using angle addition postulate, you can eventually get TUV congruent to TWV. There's a way easier way to do this proof, and the way is again using those overlapping triangles and recognizing and separating them and redrawing them and seeing what we know. So I'm going to redraw. I'm actually not separating. I'm just going to redraw this diagram a little bit. So this is W, this is V, this is U, this is T. We'll look at the diagram now. So we have these two triangles congruent by angle, side, angle. Now let's look. We already have angle 3 congruent to angle 4. That was given. CPCTC is going to get us VU congruent to VW. And now when we look at these two triangles, and again I did this on purpose because it has angle TUV in it and angle TWV in it, which is the two angles that we're trying to prove congruent. And it's got TU and TW, which we're also trying to prove they're congruent. If we look at this diagram, you have to see side angle side at this point in your geometric careers. You've got to recognize this as side angle side. CPCTC is going to get us the rest. So we were already up to here with angle side angle. And then we go UV congruent to WV, UV congruent to WV, CPCTC, corresponding parts of congruent triangles are congruent. Then we go TV congruent to TV, reflexive property, right here. That gave us the two triangles congruent by side angle side. Once we got the two triangles congruent by side angle side, these pieces, parts that match up with each other have to be congruent by CPCTC. It's a good proof because it shows again, separating and redrawing is going to help you to visualize an easier way to get to these two triangles. Example 17. Okay, AB is congruent to AC. Angle 1 is congruent to angle 2, which is congruent to angle 3. Angle 1 congruent to angle 2, which is congruent to angle 3. Okay. Let me redraw this triangle, this diagram. B, A, C. What can you tell me about this triangle? It's isosceles. What do we know about isosceles triangles? Base angles are congruent. Base angles there. That means angle B is congruent to angle C. Now, that was easy to get. Now when I go back to the original picture, I should see a pair of triangles that are congruent to each other. Angle, side, angle, angle, side, angle. Triangle BXA is congruent to triangle CYA by angle, side, angle, side, angle. Our goal is to get AX congruent to AY. AX congruent to AY. I've got them by CPCTC. 17 is a very quick proof to write out. It's a little hard to see it because most people don't recognize the base angles theorems right away. Actually, the base angles theorem that they try to go to is they try to get angle 5 congruent to angle 6, giving us a converse of the base angles theorem to give side XA congruent to side AY, which is an approach, but it's the wrong approach for this particular version of this diagram. All right, example 18. Angle 1 congruent to angle 2. Angle 3 congruent to angle 4. Okay, angle 1 congruent to angle 2. What does that gain us? Hopefully at this point we've got enough of these problems now that we start to see its isosceles. PO is congruent to QO. Converse of the base angles theorem. PO is congruent to QO. Our goal is to get angle 5 congruent to angle 6, here and here. Okay, now, two different ways we can do it. We can actually go after triangle PRS and triangle QRS, because angle 5 and angle 6 are in those two triangles. We might be able to get them eventually if we take that route, because SR is congruent to itself in those two triangles. But we don't have the complete picture to be able to get those two triangles congruent. What we do have is we have enough information to get triangle PSO congruent to triangle QRO, because we have vertical angles. Angle, side, angle, angle, side, angle. So vertical angles congruent to each other. The two triangles are congruent by angle, side, angle. Once we got the two triangles congruent by angle, side, angle, OS and OR are congruent to each other by CPCTC, making angle 5 congruent to angle 6 by the base angles theorem. It's a pretty neat proof because we use the converse of the base angles theorem, we're using vertical angles theorem, we're using angle side angle, we're using CPCTC and the base angles theorem again. Not the converse, but the original. It's an interesting little proof there. Example 19. All right. PR is congruent to PQ. Already I can't mark that in the diagram. R, P, Q, PR, PQ. I already see I've got base angles here and here. PRQ is congruent to PQR. That's probably going to be useful. SR is congruent to TQ. SR, TQ. Okay. SR is part of this triangle here, this small triangle in the middle. TQ is part of that small triangle in the middle. I don't have a letter here. That doesn't mean that we couldn't put one as the intersection of SQ and RT. We could put one there, and we could prove these two triangles congruent, probably. But it might be a hint telling me that there isn't a letter here. Maybe there's another pair of triangles that we can look at. We can look at triangle SRQ and angle TQR. SRQ and TQR. That drawing of it. Now, why am I going after those? Well, I just said angle R is congruent to angle Q. Right here. What else do we have? We have RS congruent to TQ. That's in the given. Anything else in these two triangles? Yeah, we're going back to that hint. I gotta find it again. Separate and redraw. Identify the common angles and sides. Use them with the reflexive property. So what's common? What was originally common? RQ. 1, 2, 3 is congruent to RQ. 1, 2, 3. RQ is congruent to itself. Side, angle, side. Side, angle, side. Once these two triangles are congruent by side, angle, side, QS is congruent to RT. QS, RT, CPCTC. The rest is writing it out. So rewrite the given. Angle PQR is congruent to angle PRQ. Base angles theorem. RQ is congruent to RQ. RQ is congruent to RQ. Reflexive property. Two triangles, RQS. RQS is congruent to angle triangle QRT by side, angle, side. And finally, QS is congruent to RT by CPCTC. Corresponding parts of congruent triangles are congruent. Example 20. All right, example 20. We've got angle 1 and angle 2 are congruent. Angle 1 and angle 2 are congruent. Angle 3, 2 is congruent to angle 4, 1, 2. Our goal is to get MJ congruent to NL, MJ and NL. That gives me a hint as to which two triangles I'm going to prove congruent to get MJ and NL. I'm going to look at triangle LMN and triangle JNM to get those congruent. And there's two different ways of doing this proof, and they're exactly the same amount of steps. We can do segment addition, right? Because MJ is made up of MO and OJ, and NL is made up of NO and OL. We can do segment addition. I'm going to do angle addition because I've done segment addition a couple times already in previous examples, so I'm going to use angle addition on this one. What angles am I going to be adding together? Well, angle 1 plus angle 3. Angle 1, add to the left-hand side angle 3, is equal to angle 2 plus angle 4. Angle 2, which is equal to angle 1, add to the right-hand side angle 4, because we added angle 3 to the left-hand side. We're adding equal things to the left and the right-hand side. That's the addition property. Now when we say angle addition, angle 1 plus angle 3 is angle LMN. Angle 2 plus angle 4 is angle JNM. That's the angle addition postulate. Substitute. Instead of writing angle 1 plus angle 3, we write angle LMN. Instead of writing angle 2 plus angle 4, we write angle JNM. Substitution property. I now have this pair of angles congruent. I'm going to separate and redraw the two triangles that I said I was going to go after to get MJ and NL. And N and J up here. Okay. Angle 2 is here. Angle 1 is here. So that was given information. We just proved angle LMN congruent to angle JNM. Okay. Well, what else do we have? We separated, we redrew. We have to identify the common sides and angles. What is congruent to itself before I separated? MN, MN, MN. These two triangles are congruent by angle, side, angle. Once we've got the two triangles congruent by angle, side, angle, MJ is congruent to NL by CP/CTC, and the rest is just writing it out. Rewriting the given information, addition property, angle addition postulate, substitution. Said all those already. MN is congruent to MN by the reflexive property. That's the common side. Triangle MJN is congruent to triangle NLM by angle side angle. And then what we were trying to prove, MJ is congruent to NL by CP/CTC. Corresponding parts of congruent triangles are congruent. Example 21. Example 21 is super short proof, but this is a really, really challenging proof to visualize. It's not an overly complicated diagram, although it's not a simple one. It's kind of tricky, but it is a very tricky diagram to see which two triangles we're going to go after to prove congruent. Okay, so let's mark up what we know. Angle 1 is congruent to angle 2. Angle 1 congruent to angle 2. And also congruent to angle 3. And that's going to come up in a bit. Angle 1 congruent to angle 2, that tells me that HE is congruent to HD. That's helpful. ES is congruent to DT. This is a huge hint right here as to which two triangles we're going to go after. ES, which I can't mark in my diagram, is congruent to DT, which I also can't mark in my diagram. But that's, again, a huge hint as to which two triangles we're going to go after. So, ES, and I need this, I'm going to use this angle 1, and this HE that I've just shown, they're all part of this triangle here. HES. Right? HE. ES congruent to DT. Angle 1 is down here. This is angle 4. That's one of the angles we're trying to prove congruent. Now, the other triangle that we're separating out here, HE matches up with HD. HD. I wasn't able to mark ES congruent to DT. ES congruent to DT. HE congruent to HD. This is angle 3. Angle 1 is congruent to angle 3. Side, angle, side, side, angle, side. What angle is this up here? This is angle 5. These two angles are congruent by CP/CTC. Now, I did that really quickly, but I promise you that is a very, very challenging problem to visualize. So, converse of the base angles theorem got us HE congruent to HD. The two triangles are congruent, HES congruent to triangle HDT by side angle side, and then angle 4 congruent to angle 5 by CP/CTC. Now, again, it looks super short, it looks simple, but this is a very, very challenging problem. Example 21. Let's take a look at example 22 now. Again, this is a diagram very similar to, where did we have it before? It's very similar to example 16. It's not exactly the same, but it's similar to example 16. So we're going to see that type of a diagram pop up from time to time. Here's another example. FL is congruent to FK. FL, FK. LA is congruent to KA. LA is congruent to KA. All right, our goal is to get LJ congruent to KJ, LJ congruent to KJ. And most people, when they do that, they look and they say, all right, well, I'm either going to get this triangle here congruent to this triangle here, or this triangle here congruent to this triangle here to get LJ congruent to KJ. And that's correct. But to get those triangles is a lot easier than it initially looks. A lot of students go straight for this one with some angle addition postulate stuff and segment addition postulate stuff, right? Thinking that they can do this FJ plus JA and it's going to equal FA. And that is true. You can do that, but it's way easier to do this. Watch. I'm going to redraw the diagram again, but I'm going to simplify it just a little bit. This is F, this is L, this is K, this is A. We already have here and here, here and here. If I don't put in that LJ and the KJ, look at the diagram now. Side, side, side. FA is congruent to FA, reflexive property. These two triangles are congruent by side, side, side. That was pretty easy. Why does that help us? Well, it helps us because now angle 1 is congruent to angle 2. Or, it doesn't matter which one you go after. Or you can say angle 5 is congruent to angle 6, right here and right here. I went after 5 and 6. But really, I could have gone after 1 and 2, and it's the exact same problem, it's the exact same number of steps. I'm actually going to write, or angle 1 congruent to angle 2 by CPCTC. If I go after angle 4 and angle 5 being congruent, then I'm going to need JA congruent to JA, giving me side angle side. Side, 4 tick marks. Side, angle, side, side, angle, side, because got angle 5 congruent to angle 6. If I go after angle 1 and congruent to angle 2, then I'm going to say KJ congruent to KJ. So, or KJ congruent to KJ. And again, side, angle, side, side, angle, side, side, angle, side. Either way, I'm going to show that, or I've gone after a triangle. Let's make sure I get these in the right order. L, F, J, congruent to triangle K, F, J. LJ first and last, KJ first and last. LJ, F, KJ. LJ first and second, KJ first and second. It doesn't matter which of these, it's still side angle side. Same number of steps. The end result is LJ congruent to KJ by CPCTC. Example 23. Example 23 goes on to another page here, so there are 8 steps. So let's take a look at solving this one. Example 23, we have GD is parallel to EF. A lot of students make a mistake and mark these as congruent. They are parallel. Arrows. Okay, angle GDE, which I can't even mark in the diagram. Try here, is going to be congruent to angle GFE. Again, I've already determined I'm going to have to separate and redraw here in a second. GH is congruent to EK. GH is congruent to EK. Alright, so we're going to have to separate and redraw. We're going to have to figure out a pair of sides or angles that's going to get us to eventually get DH parallel to FK. DH parallel to FK. To get DH parallel to FK, I'm going to need probably that. Alt-int angles. Converse of the alt-int angles is going to get me DH parallel to FK. All right, so if we do that, that means I'm going to have to get this angle congruent to this angle. Or I probably could do alternate exterior angles, which would be angle GHD and angle EKF congruent to each other. that's probably going to be quicker because look, I've already got some information about the two small triangles already. I got EK and I've got GH. So that's a possibility. Okay, so let's take a look and see what else we know. The fact that we have these parallel lines, I see alternate angles here. 1, 2, 1, 2. So I have angle DGE can go into angle FEG by the alternate angles theorem. How does that help me? Well, it helps me because, and again, I'm not going to actually separate as much as redraw this and make it look a little bit simpler. Oops, I'm going to redraw it better than I just did because that was pretty awful. Just going to make it smaller and a little simpler. So G, D, E, F, and I am going to draw in this one right here as well. Okay, parallel, parallel. These two angles, which is what tipped me off that I was going to be separating, redrawing already. Alternate angles. So here's my Z-like shape. Here's that Z-like shape. In this case, it's an N-like shape. It's still a Z-like shape. Okay, and if I look now at this diagram, you gotta recognize angle, angle, side. Angle, angle, side. GE is congruent to GE by the reflexive property. So I knew. So now I've got these two triangles by angle, angle, side. Triangle DEG congruent to triangle FEG by angle, angle, side. What does that gain me? What does that gain me? That gains me angle side DE congruent to side. Oh no, even better. I could go DE congruent to GF, and I could go after these two triangles, which would get me here and here the alternate interior angles. I'm going to go after the outside ones because I'm not sure if I've got enough to get DHE congruent to FKG because I would only have DE congruent to... No, I would actually have these angles too. So I could do these two. I would have this side and this angle. I would have this side and this angle. And then I might be stuck. So I might not be able to go get it that way. But if I go after these two smaller triangles, DHG and FKE, let's redraw those. There's the D, H, the G, which is, we've got that, and that's given, and bad drawings, I apologize. K, E, F, 2, and that was given. And if I now say from these two triangles being congruent by angle side, DG, 3 tick marks. This is 2. This is 3 tick marks. 1, 2, 3 tick marks. 1, 2, 3. 1, 2, 3. DG congruent to FE by CPCTC. I now have these two triangles, look at them, congruent by side, angle, side, side, angle, side. Two triangles congruent by side, angle, side. What does that gain me? Well, angle H congruent to angle K. Doesn't look like much in this picture, but angle H here, 1, 2, 3, angle K here, 1, 2, 3, they are alternate exterior angles, angle GHD congruent to angle EKF, CPCTC, are alternate exterior angles, converse. It's twice. I missed the converse piece. Gets these two lines, segments, parallel by the converse of the alternate exterior angles theorem. That was example 23. Example 24. We have AM congruent to MB, AM congruent to MB, AD congruent to BC, AD congruent to BC, okay, and angle MDC congruent to angle MCD, okay. Those are angles here and here. Okay, so again, probably going to have to separate and redraw. So we take a look. I'm going to take a look at this last piece here, what we just wrote. These two angles are congruent. This is an isosceles triangle. I've got, and I'm going to separate this triangle and this triangle. Make the diagram a little bit easier to see. A, M, B, C, D. Here and here is congruent. Here and here congruent. Here and here congruent. These angles are congruent. Base angles theorem, converse of the base angles theorem. 1, 2, 3. 1, 2, 3. Nice. You should be able to see these two triangles are now congruent by side, side, side. So converse of the base angles theorem gets me DM congruent to CM. Side, side, side gets me these two triangles congruent. How does that help me? Well, our goal is to get AC congruent to BM. Which two triangles do we want to take a look at? It doesn't matter if you go after ABC and BAD or ACD and BDC. It doesn't matter which of those two triangles you go after. You're going to get the exact same answer in the end. It takes the same amount of steps. I went after ABC and BAD. So let's separate and redraw. A, D, B, and A, B, C. Okay. We have AD, BC. We know AB is congruent to itself. We up to 4 tick marks. 1, 2, 3, 4. 1, 2, 3, 4. And if we just proved these two triangles congruent by side, 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 this angle A, which is this one here, it's 2 arcs, is congruent to this angle B here, which is this angle B over here. 2 marks. It's not this angle B. This angle B is this one. This is DBA. DBA. We just proved CBA. CBA. Which is not this one. It's this one. CBA. Congruent to DAB, which is this one. DAB. DAB. Okay. Now, side angle side. Side angle side. We finally have what we were trying to get, which is AC congruent to 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. I'm not going to put it in the diagram because the diagrams are already complicated enough as it is. So, writing it out. MD congruent to MC, converse of the base angles theorem. Two triangles, AMD congruent to triangle BMC by side, side, side. Angles were congruent. Angle DAM congruent to angle CBM by CPCTC. DAM, CBM, CPCTC. AB is congruent to itself, reflexive property. Triangle DAB is congruent to triangle CBA by side angle side, side angle side, side angle side. AC, AC congruent to BD over here by CPCTC. That was example 24. And I am not going to go through example 25. Example 25 is incredibly difficult and time consuming. And since this video is already 1 hour and 46 in 2 seconds, 1 hour and 46 minutes long, I'm not going to take the time to go through this proof. This is far more difficult than anything you will ever see on a quiz or a test. It's a great proof. On a scale of 1 to 10, this is probably a 72. This is incredibly hard. You can see that it is this many statements. It's all of this and all of this. I believe there are 26 statements here to get this proof done. This is an incredibly challenging proof, and one that we just don't have the time to go through in this video. So, thank you very much. That's it.